Good morning. Today we are going to discuss an example on Fletcher algorithm and same example you try it with Adler algorithm. Adler algorithm. So first I'll read out the statement of the example. Calculate the checksum of the following bytes, that is 2b. All these are 16-bit numbers. 3f, 6a, AF. Also show that the result is weighted checksum. Okay, this is the example what we need to say calculate, find the checksum value using the Fletcher's algorithm. Okay, in this case I will go with the flowchart which I discussed in the last class. I'll use the same flowchart and I'll work with the I'll work according to that flowchart. Fine. So we'll start with a first iteration. Okay, to start with, R value is 0. Okay, and L value is 0. R is equal to 0, L is equal to 0. You are aware regarding this. Okay, so this is what is the initialization of R. In the first iteration, what happens, you see, R is equal to 0 plus my first byte, my first 16-bit word is 2b, so that gets added and the outcome is 2b. Fine. This number is lesser than 256, so it remains as a 2b. In the first iteration itself, the L value will also going to be calculated. L is equal to R plus L. So R is equal to R plus DJ. This is the first word. Whereas L is equal to L plus R. Fine. So what is the L value? L value is initially 0. What is the R value? It is 2b. So this becomes 2b. In the first iteration, the L value is 2b. R value is, say, 2b. Now I'll talk about the second iteration. In the second iteration, what happens we will see. In the second iteration, I'll calculate the R value. It is 2b plus the next value, next data word is 3f. So it is 3f. So for your reference reason, for your understanding reason, I'll write those data words over here. My first data word is 2b, second is 3f, third data word is 6a, fourth one is AF. So I started with 2b in the first iteration. I calculated R and L values. In the second iteration, I am using 3f as a second data word that is getting added with the R. So this outcome becomes, say, after performing addition, f plus b, all this equal to a, then one carry, it becomes 6a. So R value is 6a. L value, that is R plus L. So what is the L value? Previously calculated L value is 2b. What is newly calculated R value is 6a. So if I add these two, this becomes 95. I have a calculated value, so I am writing it over here. And in the third iteration, what happens we'll see. So this process continues like this. In the third iteration, R is equal to 6a plus the new data word is 6a. 6a plus 6a, it is d4, and L value is equal to d4, say 95, that is L, and d4 is the newly calculated R value. So if I add these two things, I am going to get 669. Here one thing, you be careful, because once the addition outcome goes beyond 256, we are performing mod operation. So it is, say, the outcome is getting modded. So the value will not be allowed to exceed more than 256 here. Clear? So after performing that mod operation, I am going to be land up with 69. Fine. So next iteration, fourth iteration. Okay, R value is equal to D4 plus new, this is AF. These two will going to give me a 83 after performing a mod operation on them. I hope it is clear. Here again the sum exceeds more than 256, so we are performing mod on it and the outcome will going to be lesser than 256. And last, L value is equal to 69 plus 69 is the previously calculated L value, and newly calculated R value is 83. The outcome is EC. Okay, so the checksum is, your newly calculated checksum is L and R. So what is L value? It is EC. What is R value? It is 83. Your newly calculated checksum is EC 83. Okay, these are the 4 iterations in which your checksum is calculated. Calculated checksum is EC 83. Yes, these two are my checksum values. I hope it is clear to you. If you had any doubt, you're free to ask the questions in chat group. The second part of this example is that also show that the result is weighted checksum. To show that result is weighted checksum, okay, so that L and R that can be calculated as shown below. D here, say, which is like which shows that L is weighted sum of the bytes. Okay, so for that I'll show how exactly it will be calculated. Let R is equal to start with R, it is calculated as follows. Just to show that, say, the result is weighted checksum. For that reason we are performing the calculation as shown below over here. So R is equal to 1 plus 1 second, it is not 1. R is equal to D1, it is not 1, D1 plus D2 plus D3 plus, it's not visible, rewrite it. R is equal to D1 plus D2 plus D3 plus D4. There are 4 words. So after D1 value, you know, it is 2B, and D2 is 3F, this is 6A, and D4 is AF. I hope so. So the second part of this calculation is this. After adding all this, I'll going to get 83. Yes, so next to find the weighted checksum, L is equal to 4 into D1, this is where that weight is assigned, plus 3 into D2 plus 2 into D3 plus 1 into D4. I'll rewrite since it is not visible. L is equal to 4 into D1 plus 3 into D2 plus 2 into D3 plus 1 into D4. Yes, so after performing these, D1 value get multiplied with 4 and D2 after multiplying with 3, and after performing after multiplying and adding all these values, I'll go to get and say that is EC, and mod of that becomes EC. So weighted sum is same as that what we have calculated according to the algorithm. It is EC83. I hope it is clear to you. Okay, so this is regarding a Fletcher algorithm. In the same fashion, you can perform the calculation using Adler algorithm. Thank you. Before closing this module, we are going to analyze a cyclic codes. So, and we will find their capability by using them as a polynomials. Okay. So, for this analysis reason, I am using the following notation. Gx is the notation that is used for generator, Sx is the notation that is used for syndrome, Dx is the notation that is used for say data word, Cx is the notation that is used for code word. C indicates code, D indicates data, S indicates syndrome, G indicates generator. See, these are the few notations I will going to use to analyze the cyclic code. Okay. To start with, say you know that if my syndrome is not equal to 0, okay, so that means what it indicates is that there are one or more bits that are corrupted in the received code word. If this Sx is equal to 0, that indicates that received code word is not having error. Now, say if now I will talk about the situation where number of if no bits are corrupted, or if some bits are corrupted, but the decoder failed to detect the error. Fine. So, I am talking regarding the situation where few bits are corrupted, but if decoder is not able to detect them. This kind of a situation will arise only the selected generator, okay, if Gx, if say the selected generator and our errors, if they exhibit a properties of the type, say if my Ex, okay, that is error, if that is divisible by Gx. See, if this Ex error, if it is divisible by generator, then errors can't be caught. So, then there is a possibility that if Sx0 will not indicate that the received code word is free from error. So, if this is a case, if the selected generator, if it is capable to divide the errors, okay, if it is capable to divide the error, then the whole system will not able to detect the errors. Okay. So, there will be a situations where my generator will fail to detect the error even though there is a error in the received code word. Okay. This is the first point regarding our say generator. Next property regarding generator, that is basically here we are concentrating about the generator because generator is the one which is useful in detection of errors. So, that is the reason why I talked regarding a generator in the first case. So, the next is that if generator has more than one term and the coefficient of x0 is 1, yes, if the generator has more than one term, I am talking about my generator which consists of more than one term, and say if its x raised to 0 term is 1, this is the x raised to 0 term and it has more than one terms. Okay. If my generators are of this type, okay, it should have more than one term, not a single term generator, and if its x raised to 0 term is 1, then all the single bit errors will going to be detected. Fine. This is the second property regarding generator. So, one thing is clear, if x raised to 0 bit is 1, okay, if that term, if my generator polynomial contains x raised to 0 term, and apart from that if it has one more term, it is possible to detect the single bit errors, Now I will talk regarding a situation of say two isolated single bit errors, say for example, if this is my say code word, say I will just write some word, okay. If this is my code word, say for example, if this is one bit and this is the another bit, if there exists a error in these two bits, so in what situation generator will going to detect this error, that I will going to talk, okay. So that means like say if I talk regarding a generator is of the type gx is of the type 2 terms and x raised to 0 term is 1, then generator can surely detect a single bit error. But to detect two isolated single bit errors, I need a generator say of the type which is say having this property that if generator, if it does not divide x raised to t say plus 1, x raised to t plus 1, which is error polynomial, okay, this is my error outcome. If x raised to t plus 1, so these two are talking regarding this particular representation is for error. So if my generator does not divide this, okay, so if my generator cannot divide this, okay, where a t value is between 0 and n minus 1, okay, so power of t is between 0 and n minus 1, then all the double that isolated double errors can be detected, or isolated one bit errors will going to be detected. If this is the situation, if this is a condition, if it does not divide this, okay, I am talking of not dividing this, fine. If this generator is not dividing this polynomial, then all the say one bit errors will going to be detected. This is one more property what we expect in the generator. And the last point regarding the generator is that if generator contains a factor of x plus 1, if it contains the factors of x plus 1, then it can detect all odd number of errors, then it will go to detect all odd number of errors. Just now we have discussed a few points regarding the generator. I will just those discussions I will going to summarize to talk regarding the good generator, okay. So a good generator needs to have the following characteristics, that is, one, it should have at least two terms, okay. My generator should have more than one term, at least two terms, say this can be a generator, okay. It should have at least two terms, is it clear, okay, at least two terms. The second point is that coefficient of the term x raised to 0, that is x raised to 0 should be 1, clear, that is this particular term should exist in the polynomial, that is what is the meaning of it, yes. The third point is that it should not divide x raised to t plus 1 for t values between say 0 and n minus 1, still more specific, that is 2 and n minus 1, okay. And last point is that it should not have the factors sorry, it should have a factor x plus 1, okay. So if my generator satisfies all these four conditions, then I can call my generator is good generator. Based on these four criteria only, the standard polynomials has been say constructed. So in the last class I have shown you the set of say few standard polynomials. I will just rewrite one of them, that is CRC8. This is a standard polynomial. So why this is called standard is because it is satisfying all the four conditions just now what I have discussed. So that is x raised to 8 plus x square plus x plus 1. You see the x raised to 0 term is there, there are more than one term, and it does not have it is having a factors of x plus 1. Okay. So, these are the few conditions which it is satisfying. So, we are calling it as a standard one. So, such a standard polynomials will be used in say error detection purpose. Okay. Now, till now we have discussed 3 chapters in this module, that is multiplexing, switching, switching, and last one is say error. So, we discussed regarding error detection and correction. Okay. So, next, these are the 3 things we have discussed in this module. From in next video, we will going to start discussing regarding say DLC, data link control. Fine. Thank you.